insider threat. That's a serious problem with any kind of security device. Let's move on. We can take some more questions at the end. But these are great. These are the kinds of questions that need to be asked and are often not asked about tamper-indicating seals. Thank you. We initially thought that anti-evidence seals had to be electronic so you could have something to erase, but that turns out not to be the case. This is a very crude prototype called the magic Slate seal, where you essentially write some secret letters and numbers around the cylinder there with dry erase marker. Amazing technology, actually. So serious engineering went into that so it doesn't dry out over time. And essentially what happens is the good guys know how to dial the front end of the device. They choose one of the 6 letters in a way that as this sled at the lower right-hand corner slides past the cylinder, it erases all the dry erase marker except for the one that lines up with the slot. And so that one number is saved. So essentially it's a password anti-evidence seal. The good guys know which letter to dial in, and that preserves the information. If the bad guys just randomly open the seal, they run the risk a 5 in 6 chance of erasing the secret anti-evidence information. And if we want better odds, we simply design it like a bike lock, where you have a series of rings with slots that have to line up before the lock can open. But the idea is the secret anti-evidence is inside the seal, and the act of opening the seal without dialing in the correct combination erases that anti-evidence. So the inspection involves opening it properly and then looking to see if the secret information is there and correct. And this is something called the time trap, which we also call the Shmoocane seal, which is a great name for Shmoocon. Shmoocane is the Mayan goddess of time. Now this is an anti-evidence seal. It doesn't need a password. In fact, it doesn't even have a reader. This typically goes inside a container. It doesn't care who opens the container, the good guys or the bad guys. It uses whatever sensors make sense for that application. But once the container is opened, it displays on the liquid crystal display a time, either absolute or elapsed time, and then it authenticates that time with a 2-letter hash. Basically, there's an algorithm that computes based on the time and a secret key that's known at shipping time exactly how to compute that 2-letter hash. Once it does this, though, it instantly erases the algorithm and the secret key needed to compute the hash for future times. So the problem the bad guys have is they don't know which time to put on for when the good guys are going to later open the container. But more importantly, they don't know how to compute the 2-letter hash that would authenticate that time. So to inspect this, you simply look at the time, see if it's reasonable, and then you check the hash, which you can do by reporting back to headquarters through non-secure communications channels, or you can have a little handheld reader we've built that'll compute the hash for you, given the assumption that you know the secret key, which is different for every shipment. I've done some work with wine. Wine turns out to be a huge problem for both tampering and counterfeiting. People buy really expensive wines, drink the good stuff, put in $2 chuck, and send it back out for auction. And the wine snobs are embarrassed to admit that they got taken, and it's a huge security problem. So we've developed this relatively inexpensive device that does both tamper detection and counterfeiting. If you want to do the authenticity check, you plug it into the internet, and it calls back a virtual numeric token, and you can check for authenticity. And then the seal that's present in the cap will detect if the bottle's been opened. It's not a lock. You can take this cap off anytime you want, but that's detected as a tampering event. It turns out one of the problems is we could make this thing really, really inexpensive, and that's not good. If you're going to do wine security, there has to be a snob appeal. And so the people we were talking to really wanted this to sell for $50. We think we can make it for a couple.
I was griping about light sensors earlier. What we like better than just light sensors are color sensors. Whoa. Are we?
I think you're good.
Yeah.
Fail.
Yeah.
Next slide.
Yeah.
Let's switch it. Okay.
There we go. Okay, I looked just last night at Mauser Electronics. You can find a color sensor for $2.44. Color is much nastier to defeat than, say, light level. What you do, it takes a little bit more work. But if you colorize the inside of a volume, and you've got an acid in there, it can integrate the color inside the volume, and if that changes, hand comes in, shadow, whatever, then it trips. That's much nastier than just a light level, which you typically go for low light levels and you're doing good as a bad guy. Another thing that drives me crazy, it doesn't make sense at all. You know those little magnetic door sensors and window sensors? Those are all binary. They're either low or ground or 5 volts or 3 volts or whatever the system runs at. So either you shunt the system or you jumper it or open it up to circumvent. In fact, instead, they could use a Hall effect magnetometer, which these things are cheap, dirt cheap, and they provide an analog signal given a particular field value. So if you've got a magnet, this thing learns the field value when the door's closed. Then if a new magnet comes in to, say, spoof the system, that changes the field vector, you set off the alarm. Nobody's doing this. It doesn't make sense. Why? It's just, right now, the stuff out there is just way too easy to defeat. There are a lot of very cool sensors that could be used in security that aren't. Yeah?
I sold you a system that really worked well. I only get to sell it to you one time. But I steal your car and resell it for a lot.
Gentleman has a very good point. If somebody sold a system that really actually worked, he could only sell it one time. So that's a very valid point.
This is another type of seal we like because it's really easy. Rare earth permanent magnets are very inexpensive now. The idea is if you've got a vault or you've got a cargo hold, you're going to sprinkle a bunch of rare earth magnets at random orientations and strengths throughout the cargo or the assets. If it's cargo, you're going to glue them down and glue down the pallets so the cargo doesn't move around. But now you're going to sit outside the vault or the container and measure the magnetic field, the complex three-dimensional magnetic vector field from all these rare earth magnets. That's very easy to do nowadays with some very nice commercial off-the-shelf magnetometers. They typically have a few nanotesla resolution in comparison to the Earth's field of 55,000 nanoteslas. They have a huge dynamic range of more than 6 orders of magnitude. What this means is if the bad guys go in and move something, they have to put it back with typically micron accuracy in 3 dimensions and arc-second angular precision. Now, if you don't want to push it that far because of the huge dynamic range, you don't have to measure with that kind of sensitivity. Now, can you put things back with that kind of resolution? Well, sure, but it's kind of time-consuming, so it's not a bad approach. But we can make life more difficult for the bad guys by simply scrambling the magnets when the door is opened. Now, this isn't how you'd really implement it, but it's a very simple approach. It's what we call the hamster wheel. It's on the inside of a door, and inside is a rare earth magnet that's been potted in some clay that's multifaceted. When you open the door, the magnet tumbles on the hamster wheel. When you close the door, it goes back to a completely different position and orientation. So you can sit from outside the door with your magnetometer, measure the magnetic field, and then leave, come back later and make another measurement, determine if the magnet's moved. Now, the way you would really do this is implement it in the door jamb. When the door is closed, the magnet's trapped in some position. But when the door is open, it gets tossed like some dice, tumbles around, lands in a new position, gets trapped again when the door closes. So very, very simple kind of approach. This is another kind of using very simple materials, again, very reusable. This is what's called bead in a box. We're going to show you a technique here called the blink comparator, something from the 1890s. It's the way you find planets and asteroids. You take a picture of the night sky, come back the next night, take another picture. You then blink or show each of the 2 images in a registered mode. Anything that's different will be interpreted by the brain as movement. So what we have here is a bunch of multifaceted balls. We've got a wooden box inside there that's got the valuable asset of interest. And we simply have some foam and we squeeze the lid down. And now you're going to see a blink comparator initially with nothing happening. So there isn't too much difference between the 2 images. But then I'm simply going to open the lid. I'm not even going to reach in and grab the asset. And so you can see just by looking at this comparison of the 2 images without having to think or run complex computer algorithms that there's a great deal of difference. Bad guys have to put all these balls back right, and they can't glue them because when we open the lid, we're going to check that they are free. This is a good way to check for adhesive label seals to see if they've been tampered with. And you can tell if somebody's been messing with things on your desk. It's a very powerful technique, very easy to use if you use a kinematic